Now, what to do when you first are given this job of having to reinforce? First thing I ask for is, well, the interference, but then I say, the joists that are there, what are the web members made out of? What's their configuration? Are they rod webs? Or are they crimped angle webs? Now, I'm talking K-series joists right now. In the old days, all joists had rod webs. For the last 20 years, we've made joists that have angles, single angles, that are crimped at the ends, they're squeezed together, and they're shoved in between the top and bottom chord. Well, what difference does that make? The difference it makes is you can't slam something up next to the top and bottom chords because the web angle is sticking out. You can't weld. So you have to know whether you have rod or crimped. I can't tell you exactly when a manufacturer is going to switch from rod to web, but in general, it's around a 20-inch deep joist. If it gets to be a 30-inch K-series, it's got crimped webs today. Except the end diagonal will be a round. So there's no exact determination, so you have to find out. There are also a number of joist companies now that are not using either rods or crimped webs. They're using cold form channels for the web members. So you may encounter that. What are the chord types? Are they angles? Are they hot rolled? Are they cold formed? Might be cold formed angles. They may be a funny hat section. The bottom chord is conceivable that if you're going into an older facility, there were rod web bottom chords. The Chicago Gooder, I think, made the rod web bottom chords. I think we got away from that because wind uplift requirements. And when I first started in practice, wind didn't suck. But now it sucks big time. It's just blowing things all up. Don't blame AISC and people like that for the complexity of design today. I can't say this, I'm on national TV, but why don't you get involved maybe with ASCE 7, huh? And try to eliminate the 540 load combinations that you have to deal with on a design. I mean, there's where the complexity lies today. And it's just getting more and more complicated. And unfortunately, a lot of people like myself and Larry, we all get involved with the materials guys, and we've all focused on the resistance side of the equation rather than the load side. So you need to think, we all need to spend a little more time putting pressure on our congressman to get the load side squared away. Okay? That's my advertisement for the day. Check bridging locations. Where are they? Where is it bridged? And again, interferences. And what are the conditions of these joists? I went into a facility not too many years ago where it was one of the classic things. Somebody had put steel joists and steel deck over a swimming pool in a school. And we all know they're going to last about 5 years unless ventilated properly. And the chlorine gases went up. And before I went in the building, I walked on the roof, and I am still surprised that I didn't go through. Because when I went inside, maybe this is the tip, don't walk on a roof until you've gone inside and looked up, okay? Because there was not much deck at all. I think the tar paper was holding me up. And there wasn't much left of the joists. They had corroded so much. So I said, sorry, you're not reinforcing this. It's just a piece of junk. Tear it down and put new ones in. It was going to be cost prohibitive. So look at the condition of the joists. The owner probably found another engineer that said it'd be okay. I don't know. Okay, how do you reinforce chords, webs, seats, and welds? Thinking about force reversals, that's important. The first thing you do is determine the existing joist capacity, okay? And I refer you, of course, to the SJI load tables, which will tell the capacity of the joist. And then you can figure out from the specs maximum axial load, maximum web member capacity. You may not know the material properties, and I refer you to the 75-year digest that SJI produces. That was printed in 2003, and this has all the specifications and all the load tables for all joists that were made in the last 75 years. So if your plans that you have don't show, or your shop drawings or whatever, you don't know what joists you're dealing with, but you know the year, roughly the year, you can pretty well hone it down onto what type of joist it was, and then you can get the specifications. You can figure out whether they were using a 36 KSI steel for the chords and the webs or whatever. So that's a big asset. Sometimes there's joist tags, and the joist tag, well, there's always a joist tag on one end of the joist, but it doesn't always give you very much information. It usually will have the project number for the joist. It may not have the manufacturer's name. Okay. Since I've been involved with SJI now, I suggested they change their joist tags, and I think it's mandatory now that the manufacturer's name be on the joist tag. If it's Volcraft, it's got to say Volcraft. If it's Can-Am, it's got to say Can-Am, or what have you. So then, if you know that, and you get the job number, you might be able to call the manufacturer and say, here, this is your joist. And of course, the first thing they'll say, how do you know? You know, hey, your name's on the tag, buddy. So, okay, it's my joist. And then you say, here's the year, and here's the job number. Do you still have that information? But they can be of a big assistance in helping you determine the original capacity. If you bomb out, if you don't get any of that information, the last resort is go up and measure everything. Chords, web members, diagonals, welds are tough. You really can't measure the welds. You can get an idea of the quality. The thing you know that the joist spec has always said is that the weld has to develop the strength of the member. So you have at least that much weld. If you go to the job site and want to measure, you can only do this with a micrometer. You cannot take a tape measure because joists are ordered to 1/1000th of an inch thick in material. They just don't use 2 by 2 by quarter angles or 2 by 2 by 5/16 or what have you. They use a 1 3/4 by 1 3/4 by 0.109 or 0.232. It's not in the book. So you have to be accurate. You have to measure accurately, and the only way to do that is with a micrometer. And same with the web members. Okay, so you might also, if you want to have some fun, take the micrometer out to your job sites and measure deck thicknesses. You will always find that the deck is 0.95 times the thickness that you thought it was. Always. Because the AISI specification says that you can have a deck that's 95% of the design thickness. Now that was originally meant for these random places where some guy goes out and measures. But, oh boy, you know, the spec says that. So it's all supplied 95% thickness. And the other one that, since we're on this kick right now, is, I think you all know it now, the 2005 manual is a good one, is HSS. HSS material, if you ordered a 8 by 8 by quarter inch tube, you didn't get an 8 by 8 by quarter inch tube. The thickness was 90%. So now we've beat up on the HSS boys pretty good, and the manual now has a design thickness and a nominal thickness. Okay, so that's good to know. We used to put holes in our HSS members so that we could measure them on the job site. Once they have a cap plate on and a base plate, folks, you don't know what thickness is there unless you drilled a hole in it. But some tricky stuff. As we say in the office, this is a tricky business, you know. So existing joist capacity, you can figure the moment capacity, you can figure the shear capacity, and I mentioned the weld strength has to equal the strength of the member that the forces in the member. You can get really crazy on designing reinforcement for joists, and it can take a lot of time. My recommendation is, if you have to design some web reinforcing, design it for the total shear load that's there. Don't screw around and worry about, well, how much is the existing web taking and how much is my reinforcing taking? Usually it's not a big deal. Material is cheap, okay? And unless you're forced into a corner for some reason, just design a bunch of angles that'll take the whole load. You can also then weld them to the joist for the whole load. Then you don't have to worry about the quality of the existing welds. You don't have to worry about, you know, how long they are, how strong they are. Just go ahead and brute force. And it's all in your control then. So I recommend that if at all possible. You could proportion the load between the existing web members and your reinforcement depending on stiffness, and that's the other way to do it. And cord reinforcing, I generally will proportion the load between what the cord can take versus my reinforcing. It is more economical with the cords. Question always comes up, what about shoring? Do you have to shore when you do this reinforcing? The reason for shoring is primarily for safety, because if I start throwing a lot of heat from welding onto a joist cord, especially if the joist, let's say the joist is running this way, and I would weld all the way across the cord, I would probably generate enough heat that it's at least going to sag. If I was welding on one cord only and going longitudinally, I'm probably okay. So you can look at stresses, you can look at forces, and that's not what needs to worry about. It's more safety with the shoring. Some ways to reinforce that I'm sure you've done, but again, it gives you comfort that some other people might have done. And here's some cords. We'll put rounds in typically, if we can stuff them in there. Now again, see here's where it's important when I ask the question, was the web member crimped angle? Was it a rod? Maybe it's two angles on the outside. If it's two angles on the outside, you're not going to get the reinforcement up in there like that. So you have to know. And then you weld it, flare bevel welds. Remember, there's usually deck on top of this. That's why you can't work from the top. You have to be working from underneath. You might use angles. You can get the weld in here and there, maybe in there, depending on proportions. Here's a joist that has double angle web members. Now, look where they stop just short. They might even be touching the top cord. There's no way you're going to get those rods in there. You just can't do it. Starts and stops. So one thing we've done is we crop off the diagonal ends like that. Boy, the joist folks now, if there's any joist guys here, you're starting to get really nervous, and because, oh, that engineer is starting to cut my product up. It's your product now, right? So you can cut it like that. And now you might be able to put the rod up there and just make one flare bevel weld. So that's a possibility. We did this once. It was terribly expensive, but we needed a lot of reinforcement on a joist. Whoops. what did I do? Oh, okay. I switched. We needed to get reinforcement here. So what we did is we cut this outstanding leg off, beveled it back. We created plates that have little incisions in them to go around this material. It was terribly expensive, of course, and this is why you don't want to do it, and stuck it up there. Bottom chords, usually easy if there's no interference, because you can do downhand fillet welds. You make the plate wide enough so there's room for the weld, and it's sort of what we would call a no-brainer. Angle reinforcement, shown dotted here, would be like a rod web configuration. You can slap some double angles on each side. There's no worry about interference. If, however, you have a joist, this is a joist that has a crimped angle. Maybe you can see this one better. But see, it's sticking out here, and now it's crimped, and it comes in between the top chords. This one, you have to be a little more careful on how you put an angle on either side, because one of the reasons is you want to make sure when you reinforce that you have a work point where there's not a lot of eccentricity, or you'll start throwing all sorts of eccentricity into the top chord that it's not been designed for. Okay? So you have to be careful. We've done things where if we needed just weld reinforcement, we'll take a rod, and you can, I don't know if you can visualize this or not. Remember, this is sticking out. We roll the rod down until it hits the angle, it hits the chord here, and we'll weld both places to reinforce the weld. We have also done this. This is really kind of elaborate, where you take a plate under here and, again, add reinforcement. Anything that works, but do remember that you've got to watch out for the eccentricities up here. Outside web members like this. Now here, there's some interference, obviously, okay, on this particular job. Plus, here was a wall. So you're not going to get anybody behind that wall to reinforce on the other side except somebody that's about this thin. Okay, so that can be a problem. Web reinforcement for angles, again, we like rods. Just put a rod in there, weld it up. You may have to add some extra weld to take the forces. Worst comes to worst, we've added gusset plates. Just try to stick a gusset plate up in there, and away you go. End diagonals are also a special treat. Again, you have to be very careful about work points over here. This line of action should line up with that so there's no bending. And in the Joist Digest, we're going to cover all these things and give some really nice details for you, plus design procedures. What if the joists are too long for a project? Usually if they're too long, they're like a few inches too long. Okay. Yeah, it's obvious. Make them shorter, you know. Solutions, don't just think about the joist. Maybe it's cheaper to move the support member. Now, if it's some masonry wall that's been built, yeah, you aren't going to get anybody to move it. But maybe they're landing on a beam that's framed into a column at each end. Maybe you can change how that beam is framed to move it in or out a few inches. That's cheaper than modifying a bunch of joists. Okay, so look at the big picture, I guess is what I'm saying. Just don't get stuck, oh, I got it. Joists are too short, they got to be shortened, or too long, they got to be shortened. Look around. Maybe you can shove the footing over with the bulldozer, you know, so that it's in the right spot now. Secondly, get new joists. If time permits, again, that'll be cheaper than trying to reinforce a bunch of stuff. Again, you think of using a beam. And I say cut and replace a section in the center of the joist. My joist friends don't like that. They'd rather do it at the end of the joist. I like the center. And the reason I like the center is if I do something at the end, I'm messing around with the seat, I'm messing around with the end bar. I've got to not only cut the chord, I've got to cut, you know, the most significant end diagonal. If I do it in the center, yes, that's maximum moment, but there's hardly any shear. So I can reinforce where I cut. But it's an argument I have with them, and I think most of the time they'll say, oh, cut it at the ends. I'm sure in the technical digest it's going to show cutting it at the ends because they're paying the bill. Okay, so and you could have redesigned the joist seat certainly. If they're too short, here's some coming into a masonry wall. That's when that baby, I'm not sure it's even touching there. It's just barely in there. That's when you get the joist stretcher, right? You just pull it, make it longer. Come on, guys, wake up. It's lunch. You know. Just think of the poor guy trying to pick up CEUs watching this tape. Huh? He's asleep now, or she's asleep. Going, oh, I got my CEUs. Okay. But there's a test, you see. So joists are too short. You got to make them longer. Same ideas. New joists, use a beam. Extend the beam flange possibly, modify the joist, splice the joist if you want, move the support member. All those same things can be done. I just show you this because it's a relatively common error on framing diagrams. Here is some joists, 28K10s. The framing kind of changed here. Here's a 16 by 31 that goes from that column to over here to another beam. And the engineer put this joist in here, 28K9, and framed it in, probably because we engineers are hung up on symmetry. You know, we like to see things, parallel lines going along. So here he did that. Now what that happens is, if this joist comes in at an angle that is 30 degrees or less, I can guarantee you're going to have a bearing problem. It's not going to fit. Okay? So don't do that. Don't frame it that way. Frame it maybe this way, where now you would take the same 16 at 31, it's still going the same place, and move this so it's over here. It didn't have to be parallel. You know, it's cost the erector a little bit of time maybe to find out where he's supposed to put his weld, and probably get a few more blowholes through the deck, but that's a much better way of doing it. Bridging, often asked. What to do about bridging. Here I've shown some X bridging and some sort of duct work needed to go in. And yes, it's permissible to cut that X bridging so long as you X bridge on either side of where it's cut. It's okay to cut a top chord or bottom chord bridging so long as you X bridge on either side of the cut. Those forces, there are forces in bridging. There are forces in bridging even after the building is built. Most people think, oh, the bridging is there for construction to stabilize the joist. Wrong, wrong, wrong. It does more than that. It's there for lateral bracing for wind uplift on the bottom chord. It's there to laterally stabilize the web system. Think about it. If you were designing a truss, let's take a truss. You're not a joist designer, but you're designing a truss. And you're designing some web member in that truss, okay? Some diagonal member. Maybe it's 6 feet long. I don't care how long it is. Goes to a top chord, goes to a bottom chord. You take an effective length factor out of plane Well, in plane first, say it's 1, okay? Out of plane, you take 1. As soon as you take K of 1, what have you said to yourself? That it's laterally supported at the top and at the bottom, in and out of plane. What laterally supports it at the tension chord? The stiffness, the lateral stiffness of the tension chord. And remember, bracing requires 2 things, strength and stiffness. The bridging stiffens up the bottom chord out of plane. So it's very important. It's very important for the end compression diagonal because that has the biggest force. So if you really think about what's the truss that's got top chord and 2 diagonals and a vertical? King post truss, I think. You would never let that bottom piece hang in the air. If you get the load a little eccentric, it's going to flip it over. So be careful with just saying, yeah, you can remove the bridging. I have a great story on joists. Actually, there's 2 stories. I'll bore you with, I may forget the second one. The first story is, and you'll love this. I know the fabricators will love it. This was in Houston, Texas. There's about a 100-foot run of joists, every 5 foot on center, coming into a beam. Our friendly HVAC guy finally gets his act together and he figures out where he wants his duct. Okay. He wants his duct right where the end diagonals are. Of course, he wants them next to the beam. There's more space if you get them up in there. So what does the contractor do? Well, the duct's supposed to go here. There's a joist there. Well, let's just cut the end diagonal out of 20 joists. No. Put the HVAC system in. Good as gold. Calls up the fabricator. Say, Mr. Fabricator, you had a member in there that was in the way of our ducts, so we had to cut these members out and put the duct in, and I suggest maybe you better take a look at those joists. Good thing he called. Okay. Fabricator goes out with the erector, sure enough. Every one of the 20 joists are cut. This is a true story. Oh, okay. Let's torch a hole in both sides of the duct, shove the end diagonal back in, weld it up, which he did. Called the HVAC, hey, duct is whistling like crazy out there, you know, that thing isn't working. So next time the guys that are here, if that happens to you, just cut the duct, shove it back in there, and I think that nonsense would stop, okay? It's a beautiful story. Same city, I know they put some joists in a building, and this had to be a really bright people. Well, can't say it. They put the joists in upside down. The only thing I'll give them, they were bottom-bearing joists, so, you know, they look the same. Turn them right upside up. You'll see this detail in SJI book. You'll see it more in the OSHA requirements. And you'll see it in OSHA that says when you get to a wall and you have expert, you have to terminate the bridging with an X here. Don't do that, folks. Okay, even though OSHA says so, don't do it. Because you're in snow country here. And what's going to happen if this joist wants to deflect due to roof load? The load's going to go up this diagonal. That's the stiffest way, or it's going to go down, and it's going to pull break the welds, pull the thing right out of the wall. So what you want to do is terminate the bridging always with 2 horizontals to the wall. They'll just bend. They won't break. So don't use that detail. Another thing,